Okay. Hello, everyone. My name is Khushi Pandey, and I'm a chemical engineering sophomore from Arizona State University. Just a fun fact, I also have minor in astronomy, so that's completely different. So my topic to present here today is silicon oxycarbide PDCs, which in my opinion is a very umbrella term considering all my research at ASU and the very brief research that I know shadowed at TU Darmstadt. So yeah, so just going over silicon oxycarbides, they have the chemical formula of SiOX, C4-X, and their ceramic materials, they have silicon oxygen and silicon carbon bonds, but no carbon oxygen bonds are formed. Below here are the images of the Sioc precursors, and yeah, essentially it's just the image. There's nothing to explain in this. The preparation is that we take the starting material, which is generally the precursors, and then we thermally convert it using pyrolysis at super high temperature. In this case, it was 900 to 1800 degrees Celsius in an inert atmosphere, which is argon. That I noticed, and the temperature of pyrolysis, heating rate, dwelling time, and the type of gas that is used in the inert atmosphere helps us find the final chemical and phase composition of the SiOC fiber. Also, high molecular weight is required for the mass that is lost in pyrolysis. And over here is an image of the different classification of SiOC fibers. So we only use certain jobs to read at least what I researched in. And here are the general results for the NMR and XPS spectra. They have been taken from the journals that are cited at the end. For the original data, please wait for Jersen's presentation, which I have no clue is when, but he has the original data of all our work findings, and I wasn't able to submit them over here. So yeah. And this is, again, some general data from journals. The original is with Jersen, so please direct all your questions to him about this. Now we go into my research, which was very brief at TU Darmstadt, which was core shell nanocarbon silicon nanoparticles. Really long name, but they can be called OLCs, or onion-like carbon with silica shell coatings. So they're mesoporous particles, which essentially means that they have really small, about 2 nanometers to 50 nanometers of coating, and they're uniformly shaped nanocomposite particles. They have a large surface area, which I think can be seen because they're nano, and the design is for drug delivery and similar biomedical purposes. So the synthesis, which was what I was shadowing with Dr. Mara's students, was this. So we had the pyrolysis of the nanodiamond sample at 1800 degrees Celsius, then we analyzed the sample, and then we have the functionalization in an acidic environment. And then we did, the last one is the modified Stover process for the addition of silicon dioxide into the core of OLCs so that they can become what we wanted them to. And then we have the centrifugation and the dissolution process to obtain the purest form of nanodiamond with silicon dioxide coating. And yeah, the heating chamber was used to dehydrate. And then a reference sample was also made in a similar way. So these are the images of me working in TU Darmstadt. So that is the pyrolysis chamber with an argon setup. That is the Stover process for the reference sample. These two are for the nanodiamonds. I wasn't present for this, but I was lucky enough to see the process of the reference, and that helped a lot. And this is the centrifugation process and the dehydration. And some notable changes that after pyrolyzing at 1800 degrees Celsius is that ethanol, which is used to dissolve as the organic solvent, does influence the thickness of the porous layer. We also noticed that from nanodiamonds to OLCs, it changes the hybridization from sp3 to sp2, and it changes its shape from a spherical nanodiamond to polyhedral shape with the addition of silicon dioxide. And the chemisorption that way becomes way more higher, thus making it very useful in biomedical purposes. So to give a brief overview of what I was doing, was that we had nanodiamonds, which we converted to bulky nanodiamonds, and which we converted to OLCs, or onion-like carbons. And this is a picture of the students that helped me at TU Darmstadt. They are grad students of Dr. Gabriela Mera, Mr. Mirza, and Ms. Naya. And yeah, they have been, you can see Ms. Naya, she's just sitting near the centrifugation thing. And I was like, you know what, I need a picture. So that was that. And these are the references from which all the graphs are taken. Thank you so much. That was super short.
I have a question.